So in this video about waves, we're going to discuss something called the Doppler effect. Now the Doppler effect occurs when a source or an observer is moving relative to the medium that transmits the waves. And as you can imagine, if you're moving through the medium where the wave fronts exist, you will encounter the wave fronts at an increasing or decreasing rate, depending whether you're moving into the wave fronts or away from the wave fronts. Similarly, a source that's producing the wave fronts will increase or decrease the distance between wave fronts, depending on its direction of motion as well. So to understand how that affects the frequency and the wavelength of the waves that are produced, let's have a look in the detail at the maths behind this. So here we have a wave source that's moving through the wave medium, and we have an observer who's also moving through the medium and observing the source. So the wave source is emitting wave fronts, and the time between it emitting those wave fronts, delta t here, is simply 1 over the frequency of the source. Now what happens is, normally if the source was staying stationary, the distance between two adjacent wave fronts would be given by lambda s here, the source wavelength. However, what happens is it emits one source, and then within this time period before the second wavefront is emitted, the source has moved some distance, which causes the wavefronts in front of the source to bunch together and the wavefronts behind the source to expand out. So the question is, due to this motion of the source now, what is the distance between adjacent wavefronts in front of the source in the direction that they're heading towards the observer? So this observed wavelength now is going to be equal to the normal distance minus the distance moved by the source. Well, the distance moved by the source is just going to be the velocity of the source multiplied by the time between the two wavefronts being emitted, which is just 1 over fs. So this is our observed wavelength now due to the motion of the source. So now the observer, of course, is looking at these waves coming in, and the observer will see the waves traveling with a wave velocity that is equal to the velocity of the waves relative to the medium, so that's going to be c. But now, since the observer is moving relative to the medium, the waves will be approaching the observer even faster, and so he or she will observe the waves traveling with a velocity of c plus v0. Now, we know that speed and wavelength and frequency are related by the equation c equals f lambda when we're talking phase velocity here for the wave speed. Now, if I do that for the standard source, if we're assuming the source now is stationary, then I'm going to have that c, the wave speed relative to the medium, will be equal to the frequency of the source times the wavelength of the source, and so therefore the wavelength of the source lambda s is simply c divided by the frequency of the source. Now I can take this quantity and I can put it into this equation here, and what that will give me is it will give me c over the frequency of the source minus the velocity of the source over the frequency of the source, and I can simplify that by taking out 1 over the frequency of the source, and then I have just c minus vs. So now I've got an expression for the observed wavelength, and I've got an expression for the observed wave speed or phase velocity. So what I'm going to do now is put these together to calculate the observed frequency. So here are the expressions we've got for the observed wavelength and the observed wave velocity. And so I'm going to use my equation here that the observed wave velocity must be equal to the observed frequency multiplied by the observed wavelength. And so that means that my observed frequency must be equal to the observed speed divided by the observed wavelength. So if I write this out now, well, my observed wave speed is going to be c plus v0, or VO, multiplied by 1 over the wavelength, which is now going to be f of s over c minus vs. And so that will give me an observed frequency that's equal to the source frequency multiplied now by c plus the velocity of the observer divided by c minus the velocity of the source. And so this is the Doppler shift formula. Now it's important to note here that VO and VS are positive for motion towards each other. So what that means is that VO is positive if you're moving towards the source, VS is positive if the source is moving towards the observer. Now, the other thing to note is that if we're only dealing here with velocity towards or away from each other, if the source is moving in this direction, then there is no Doppler shift. So in this case, FO would equal FS, because as far as we're concerned here for the Doppler shift, the velocity of the source, this is the velocity of approach or the velocity of separation if it's got a negative value. So this is the Doppler shift formula for non-relativistic waves. So to demonstrate the effect of Doppler shift with mechanical waves, what I've got here is a beeper. So we're going to use sound waves to demonstrate the Doppler effect. Now, what I'm going to do is I'm going to whirl this beeper around my head. The beeper generates a single tone. Now, when I whirl it around my head, the microphone, as you can see, is attached to me. So initially, when I'm using this microphone, you shouldn't hear any change in frequency because as it's moving around, there is no motion towards or away from this source. So what you will hear is something that's very close to a continuous frequency. So hopefully the microphone picked up what I was hearing, and that was a roughly continuous tone. There was a little bit of a fluctuation due to a slight sideways motion, but hardly anything. So you should have heard almost a continuous tone. Now what we're going to do is we're going to do the same thing, but I'm going to disconnect the wireless microphone and you'll hear it from the camera microphone, and that should show the Doppler effect, because when we're on this side, the source is moving away, and when you come round to this side, the source is moving towards you. So here we go again. As you can see, I've unplugged the microphone and probably sound a little bit fainter now because the microphone's quite a distance away, but you should be able to now hear the Doppler effect when I whirl this around my head. So now you've heard the Doppler effect for sound, and we've described it for any mechanical wave where you're moving relative to the medium. What about light waves? Light waves don't have a medium. They transmit themselves through the vacuum, and as we know from relativity, you can never measure your speed relative to the vacuum. And so for light waves, we have a slightly different Doppler shift frequency, and the formula is not quite the same as it is for a mechanical wave, because you cannot measure velocity relative to the medium. And it turns out that Doppler shift for electromagnetic waves is a very important application. It's the one that we probably encounter most often. It's the physics behind police speed radar traps. So to see how that works, let's have a look in detail at the maths behind a Doppler shift for electromagnetic waves. So here we have a diagram that's going to let us calculate the relativistic Doppler shift, and since we're talking about waves like an electromagnetic wave here, we have no medium to measure our velocity relative to. You cannot measure your velocity relative to a vacuum, and so we only have one velocity, and that's the velocity of the source here, measured relative to the observer. So since we're going to have now two inertial reference frames, one for the source and one for the observer here, we're going to define Ts as the period of the source in its own reference frame, and delta Tp here as the time between the production of wavefronts in the observer's reference frame. And what we're going to evaluate is the time now between the observer seeing two adjacent wavefronts. So how much time passes between the observer seeing two adjacent wavefronts. So that's going to be equal to the time between the production of the wavefronts, but then we're going to have to add on to that the propagation time, because the source produces the first wavefront here, and then it's moved to here before it produces the second wavefront. Now, if this time is a small value, which it will be for visible light, then we can approximate this distance, this extra distance that it's going to have to travel from the place where the second wavefront is emitted to where the first one was emitted. We can approximate that by just assuming that this is a right-angled triangle and taking the cosine of the velocity to give us the component of the velocity directly away from the observer. So in this case, the component of the velocity away from the observer is going to be v cosine theta, and the distance we're going to travel is just delta tp times that. So that's the distance that we've traveled away from the observer, and then the additional time delay that that's going to add to the second wavefront is just this distance divided by the speed of the waves, which is c. So this is the time between the observation of two adjacent wavefronts by the observer, and that's counting in the propagation delay because of the motion of the source. And we can simplify this a little bit by factoring out and taking a delta tp here, and then I'm going to have 1 plus, and then I'm going to say beta cosine theta here, where beta is equal to v over c. Okay, so this is the time between the observation of electromagnetic wave fronts. But we want to calculate this. Well, to do that, we have to look at time dilation. This is really just the period of the source in the observer's frame of reference, and since we're talking about now the time between two events at the same point in the source frame of reference, because that's where the source is stationary, so we're having the time between two events that occur at the same position in space, we just use time dilation, and so delta Tp is just gamma times the wave period of the source in its own frame of reference, where gamma here is equal to 1 over the square root of 1 minus beta squared. This is the relativistic boost gamma. So if I put these together now, all I'm going to do is I'm going to substitute delta Tp into here, and what I'm going to get is I'm going to get that T0 here is equal to, and what have we got? We've got gamma Ts times 1 plus beta cosine theta here. And now I want to convert this into a frequency. Well, first of all, I'll expand out for gamma. So what this will give me is Ts, and then I've got 1 plus beta cosine theta, and then all over the square root of 1 minus beta squared. And so if I convert this into a frequency, I just use the fact that the observed frequency is equal to 1 over the observed period, and so here now my observed frequency is going to be 1 over Ts. Well, that's just the frequency of the source here, and then that's multiplied by the square root of 1 minus beta squared all over 1 plus beta cosine theta. So this is the relativistic Doppler shift formula, and you can see that it's very different to the non-relativistic formula. Not only that, but in fact it depends on the direction of the velocity as well. So it's no longer we're going to get zero Doppler shift if we have no motion towards or away from the observer. And the reason for that is because we have time dilation. So even if the source is moving in a perpendicular direction, so it's not approaching the observer, it's not moving away from the observer, it will suffer time dilation, and so the frequency of the source will appear to be less than it is if you were in the source's frame of reference. So to look at these special cases, let's flip over the page and examine particular values for theta. So here's our general relativistic Doppler shift formula that we just derived, and what we're going to do now is we're going to look at the special case where theta equals 0, and so that means that there's motion directly away from the observer. And if theta is equal to 0, then cosine of theta must be equal to 1, and so our Doppler shift formula becomes that the observed frequency is equal to the source frequency times the square root of 1 minus beta squared over 1 plus beta. Now, I'm going to write this out in a slightly funny way now, and you'll see why in a second, so that this is equal to the source frequency, and then here I'm going to expand the square root, and I'm going to factorize out this 1 minus beta squared into 1 minus beta times 1 plus beta, and then this is divided by 1 plus beta. But I can write this in a slightly strange way. I can say that this is equal to the square root of 1 plus beta squared, right? Because that'll just get rid of the square root. But the reason for doing this is that I can now cancel this square root of 1 plus beta with this one, and I'm left with the expression that the observed frequency is equal to the source frequency times the square root of 1 minus beta over 1 plus beta. And so this is going to be my Doppler shift formula for motion directly away. So remember here that beta is equal to v over c. So what that means is that v and beta are positive for motion away from the observer, and they are negative for motion towards the observer. So if I have motion towards the observer, this is going to be 1 plus beta over 1 minus beta, and you can see that because in this case then if it was motion towards, theta instead would be equal to pi, and that would give me that cosine of theta was equal to minus 1, so I'd have 1 minus beta on the bottom here, and then I'd be cancelling this 1 minus beta on the top with a 1 minus square root of 1 minus beta squared on the bottom. So this is the formula for motion directly towards or away from the observer. So when we're dealing with relativistic waves, most of the time we have velocities that are a lot less than c, and this means that beta is very close to 0, and this can cause rounding errors if you're using this formula, because you get 1 minus a number that's very, very small, and that's a very good recipe for your calculator to have rounding issues. So when we're in the approximation that v is a lot less than c, we want to do a series expansion of this. So to do that, I'm going to write this out, and I'm going to say the observed frequency is equal to the source frequency, and now I'm going to have 1 minus beta to the half times 1 plus beta to the minus a half. So that's just this same formula written out. And then I'm going to do a series expansion of this to order beta squared. So we're doing this to order of beta. We're neglecting terms of beta squared or higher. So if I do this, what I'm going to have is I'm going to have the source frequency here, and then I'm going to have 1, and then it's going to be minus a half beta plus order beta squared terms. And that's going to be multiplied, again the minus sign from this minus beta here, this is going to be multiplied by 1, and then I'm getting a minus sign here because it's minus a half times beta, so this is going to be minus beta over 2 again, and then plus order beta squared. Right, so that's just the Taylor series expansion. It's for around beta is equal to 0. And we're neglecting these order beta squared terms. So if I multiply these two brackets out now, what I'm going to have is I'm going to have this equal to the source frequency. Well, I get 1 times 1, so that's going to give me 1 here. I'm going to have 1 times minus beta over 2, and I'm going to have minus beta over 2 times 1, so that's going to give me minus beta. And then every other term is going to give me beta squared or higher. Right, because if I've got 1 and I multiply it by this, I get beta squared. If I multiply beta by either of these terms, I'm going to get beta squared, or even worse, beta cubed. And again, of course, this multiplied by anything will give me beta squared or higher. So what this gives me is that if I'm making the approximation now, that I have the observed frequency is roughly equal to the source frequency times 1 minus beta, and that's to order beta, right? So we're neglecting terms higher than beta. So what I'm now going to write this out is in terms of the change of frequency. So the change in frequency is equal to the observed frequency minus the source frequency. So what I can do is I can bring this over here. So I'm going to have that delta F is roughly equal to the source frequency times minus beta. And so if I rewrite that out, what I get is that the change in frequency divided by the source frequency is roughly equal to minus V over C. And so this is the Doppler shift for V a lot less than C, and V being positive for motion away. And obviously if you have motion away, it's going to lower the frequency or lengthen the wavelength, and so that's why you have a negative change in frequency. If it's motion towards, then V will be negative here, and you'll get a positive change in frequency. So that's it for motion towards or away from, but we have this additional effect with the relativistic Doppler shift of motion that's transverse to the observer, which doesn't occur with the classical Doppler shift. So let's now have a look at that. So here's our general relativistic Doppler shift formula, and now we're going to look at this special case where we have the transverse Doppler effect, which only occurs with relativistic waves. So here what we're doing is we're looking at the motion of the source that's perpendicular to the observer. So there's no approach nor increase in separation of the source to the observer. It's purely a transverse motion, and so theta here is equal to pi over 2, and that means that cosine of theta is equal to 0, and so our observed frequency is simply the source frequency times the square root of 1 minus beta squared. Now another way to write that is we could write that as the source frequency over gamma, and that actually gives you an idea of what's causing this. This is due to the time dilation effect. So for the observer, the time of the source is passing at a slower rate, and so therefore this reduces the frequency of the source, and obviously this doesn't occur in the classical Doppler effect. So we've got this expression now, and this is our expression for the transverse Doppler effect. But you can see here that we've got it of order beta squared, and this means that this effect is, generally speaking, far, far smaller than the effect of moving towards or away from an object when beta is a lot less than 1. So let's again look at our expansion. So we're going to do V here is now a lot less than C, and so what we're going to get is we're going to have that the observed frequency, and now we're going to do this to order beta squared. And the reason for that is because we can't do it to order beta because there are no beta terms. We have to do it to order beta squared. So this is equal to f of s, and then we've got 1 minus beta squared to the half, and so if we expand that out, we're going to have the source frequency times 1, and then we're going to have minus a half beta squared, and then we're going to have terms of order beta to the 4th. So those are the ones that we're going to neglect. And this gives us that f of 0, if we make this approximation, is approximately equal to f of s times 1 minus beta squared over 2. And if we do the expansion now, we're going to alter this around and say that the change in frequency is equal to the observed minus the source frequency. And so what that gives us is that the change in frequency divided by the source frequency, so I subtract an f of s here, and then I've got an f of s times beta squared over 2, so I divide by f of s, is roughly equal to minus, and then I'm going to expand this out, v squared over 2c squared. And so this is our transverse Doppler effect. Now notice here it is always a negative. And the reason for that is because it's a time dilation effect. It doesn't matter whether my source is moving in this direction or this direction. Because it's moving relative to the observer, there is a time dilation effect that will slow down the frequency, or reduce the frequency of the source. And so this is always going to be negative regardless of which direction v is. And in fact, you can see it here. It doesn't matter whether v is positive or negative because we've got v squared here. So you're always going to get a negative change in frequency. The other thing to note, of course, is that this is v over c squared, and so it is very small effect for typical everyday velocities, and it's far, far less noticeable than the effect that we get for motion away from or motion towards the source, towards the observer. So there we have the Doppler effect for light waves, and the secondary effect that we don't have for mechanical waves, the transverse Doppler effect, which comes about due to the time dilation effect, which slows down the frequency of vibration of the source. Now we've completed all the topics we're going to discuss in waves, but this last topic has given us a nice introduction to the next thing we're going to discuss, which is light waves.